for all students. You don't have to bring a document for the discussion hour. But you have to come, only then can you discuss. So, why do we non-dimensionalize Navier-Stokes equations? There is, of course, a hope that we can simplify and obtain analytical solutions, or at least solutions very quickly. That's one purpose. The second aspect is it helps you enforce the principles of similarity. How? Well, one way of seeing it is the governing equations carry Reynolds number. So, two different flow fields, maybe air, water, oils, two different contexts. It could be air and air also. Two different contexts, but the same Reynolds number will give you the same solution in dimensionless form. So, that means two different flow fields with identical Reynolds numbers will have identical solutions in dimensionless form, which is the principle of similarity. So, non-dimensionalization enforces principles of similarity. So, if you have a cylinder in the model, you will have a cylinder in the prototype. That is taken care of through boundary conditions. You are going to apply the boundary conditions on the surface of a cylinder, and that is geometric similarity, and you enforce dynamic similarity by requiring Reynolds number to be the same. How does maintaining Reynolds number enforce dynamic similarity? Because Reynolds number in turn is a ratio of inertia to viscous forces. So, the relative importance of forces is preserved going from the model to the prototype. So, here you may add that matching Reynolds number enforces dynamic similarity. And through boundary conditions, you enforce geometric similarity. So, as a result, the solution obtained in dimensionless form carries over from the model to the prototype. So, this is now happening in the framework of Navier-Stokes equations. Earlier, we did that in symbolic form. We said let drag be a function of rho, u, mu, etc. Now, that functionality is specified. How? Through or in the form of a solution of Navier-Stokes equations. So, using scales capital U for velocity, L for the linear dimension, Navier-Stokes equations, including the mass balance equation. So, this is the non-dimensional form in using the vector representation of the gradient operator del. You can't solve this system, for that you have to go into the specific coordinate system, Cartesian or cylindrical. So, del has to be represented in that coordinate system, then you write out the equations. Now, in each coordinate system you have a slightly different method for obtaining the solution. You may remember from your mathematics courses that in Cartesian coordinates you get sines, cosines as the basis function, and you get Bessel functions in cylindrical coordinates, Legendre polynomials in spherical coordinates. Now, we decided not to go very deep into those PDE techniques. Those are available in books on engineering mathematics. Now, looking at some limiting cases. So, in books they may say RE going to 0, but that is not as specific as saying RE is small compared to 1. RE is a dimensionless quantity. So, if you want to say RE is small, it is relative to unity. If you say RE is large, it is relative to unity. Okay, so that assumes that you have picked the scales capital U and capital L suitably. So, in the limit of low Reynolds number, then you know RE is interpreted as I over V. So, I is relatively less important. I think one student correctly pointed out last time that in fully developed flow, I meaning inertia forces are identically 0 because acceleration is 0. But here the discussion is inertia forces are not 0, but small compared to viscous forces. So, then the system of equations minus gradient of P this system is called Stokes equations. So, Stokes equations of course are a subset of Navier-Stokes. Navier-Stokes is most general, Stokes is a special case, but it is an interesting special case because it is a linear system, linear in the mathematical sense. Now, usually to solve this problem, we do a del dot of the momentum equation. When you do that, del dot del is del square P, and then del square U, you can interchange del dot and del square, that gives you del dot U, which is 0. So, when you do del dot of the momentum equation, you get del square P equal to 0, which is Laplace equation, which you may again remember is a well studied governing equation. So, the advantage with this approach is you can solve for P, substitute for P in the momentum equation, get velocity. So, it gives you a very clean procedure for finding the flow field, both velocity components and pressure. So, okay, now let us look at the other extreme of high Reynolds number. Of course, low Reynolds number you would get if velocity is small, dimensions are small, viscosity is high, and in contrast you get high Reynolds numbers if velocity is high, linear dimensions are large, and viscosity is small, typically gases. So, low Reynolds number limit is typically in liquids and high Reynolds numbers in gases. So, under these conditions, inertia over viscous would be much greater than 1, which means you can neglect viscous. Do a first approximation. Which is equivalent to setting viscosity equal to 0. So, such a flow field is also called, you know from your earlier studies, such a fluid is also said to be ideal. Why ideal? Because if you set viscosity equal to 0, losses go to 0. There are no losses taking place. No loss indicates most gain, so which is desirable in any context. So, now dropping viscous terms, the governing equations set mu equal to 0. This system is often called the Euler equations. So, Euler equations are definitely non-linear through the non-linear acceleration terms. Right? U dot del u is a product of velocity and its derivatives. The system is also coupled. So, it is not readily apparent as to why this would be a simpler system compared to Navier-Stokes. But one can show that indeed it is a simpler system. Let us define just to keep the discussions simple. Let us restrict our attention to 2 dimensions and define a quantity called vorticity given a symbol omega. Which is del cross u dot k. That means it gives you the cross product k with x y as the plane of the flow, and when you do a dot product with k, k is the z direction. So, if you do the cross product of the momentum equation and dot k. So, that will give you a scalar equation like del square p equal to 0, del dot reduced the vector equation to a scalar equation, do a del cross and then do a dot product with k. So, you get a scalar equation. Del cross of del p is 0. You can see that it eliminates p from the equation by doing this del cross, and you have del cross of the left hand side, a little bit of vector calculus once again. What is the first term? First term is the derivative of del cross u with time. There is also a dot k, which is omega. So, this left hand side reduces see u is a velocity field. So, omega is a vorticity field, it is distributed everywhere. You get an equation for omega. Okay. How does it help? What you want would be the velocity field. So, let us look at a relationship between vorticity. So, you see the relationship between vorticity and velocity here, omega is del cross u dot k, but in component form omega is equal to so, you substitute for del as the derivative with x and y and u as the x and y components of velocity. So, it is just this cross product, okay, dot k. So, which we write in shorthand notation as V x minus u y. What does it symbolize? So, it symbolizes just going back to the deformation of a fluid element. Why deformation? Because if you remember, V x plus u y was the deformational strain rate of the element. It was deforming in both directions. There was some angle delta 1, delta 2. This was the deformation of a fluid element, this was angle delta 1, this was angle delta 2, and delta 1 plus delta 2 time derivative divided by 2 was the deformation rate of that element. But now, since it is a negative sign, delta 2 minus delta 1, this is interpreted as delta 2 dot minus delta 1 dot, which is the net rotation of the fluid element. This is not solid body rotation, it is the rotation arising from deformation, net rotation of the fluid element. Okay, so, in Newton's parallel plate experiment, when you move the top surface relative to the bottom surface, an element like this deforms and there is a rotation. It is getting rotated because it is because of the shearing action. Now, you can imagine that if viscous forces are very weak, then the shearing action will be minimal. Okay. But that result can also be seen from the vorticity equations. So, we are looking at, so let me just write again, in the limit of R e much greater than 1, which is approaching infinity, which means mu equal to 0, we have the vorticity equation. Equal to 0. Now, if you recall your discussion on total derivatives and partial derivatives, Eulerian form versus Lagrangian form, the left hand side can be written as sometimes called the material derivative or the total derivative d omega dt equal to 0. So, as a fluid particle moves from point A to point B, A to B, partial derivatives are evaluated at an instant of time or at a point. Total derivative is evaluated along the flow path, A to B with the limit B approaching A, along the particle or the fluid particle trajectory. D omega dt is 0. What does it tell you? That omega does not change as you go from A to B. So, you have omega b equal to omega A, no change in omega. Okay, now, let us look at a simplified flow field. Let us say you have uniform, this is a uniform flow field. In a uniform flow field, let us say this small u is equal to capital U and small v is equal to 0. So, omega, which is V x minus u y, is equal to 0. And then you also have omega b equal to omega a. So, in a very high Reynolds number flow, you see that the vorticity of a particle is conserved, it is constant. And more specifically, in this uniform flow field, it is 0, omega is 0. Now, let us say you have disturbed the flow in some manner. So, this is a disturbance. So, this flow will go around the object, but omega b is equal to omega a. So, even at a point such as P, omega is 0. So, omega is 0, P is any point, therefore, every point everywhere. So, what it tells you is that let me put an exclamation mark. Instead of solving the Euler equations, you now solve omega equal to 0, that becomes your governing equation. So, you can solve. So, let us say this now becomes your system of governing equations. So, let us write it in Cartesian coordinates. U x plus v y equal to 0 and v x minus u y equal to 0. You have a system of linear equations in u and v. You can solve these two. There is no complication of pressure, there is no pressure in this equation. So, you have succeeded in drastically simplifying Navier-Stokes equations, then take a limit R e approaching infinity, set mu equal to 0, look at the vorticity equation and replace momentum equation by vorticity equation. Of course, it holds only when, so this system will hold when the approach flow is uniform. Okay, you have a uniform approach flow. So, this approach will become this strategy will become clear when we look at some examples. So, it now remains to find pressure. We still have to find pressure. So, for that we have to go back to the momentum equation that contains pressure. So, still talking about the mass balance equation, the vorticity equation, and now to find pressure we go back to the momentum equation. Let us say, just for so, this is the momentum equation where I have just dropped the time derivative just to keep the calculations a little simple. But by the time you reach the momentum equation, you already know the velocity field. So, it is no complication here. Velocity, that nonlinearity has no meaning because you know the velocity distribution by solving mass and vorticity. Okay. So, this calculation is carried out. So, let us say this is the particle or the fluid path or the streamline in our discussion. And let us say this is the s direction and this is the normal direction. So, the velocity component parallel to s is capital U, let us say it is capital U. Okay. And what is the velocity component in the normal direction? If that is a streamline, velocity normal to the streamline is 0. So, normal component. So, now if you work with S n coordinate system, there is only one velocity component. So, this momentum equation can be written as rho along the s direction. So, by integrating the momentum equation, you get the simple result p over rho plus u square over 2 equal to constant. What is capital U? It is the velocity component along the streamline. So, the constant will depend on the choice of the streamline. So, let us call this, see the streamline is defined by a stream function psi. So, this constant will depend on the choice of the streamline. Now, what is this equation? Have you seen it before? What is this equation? Bernoulli's equation. So, when do you get Bernoulli's equation? For ideal fluid flow, where mu is 0. So, you see that Navier-Stokes equations will reduce to Bernoulli's equation in the limit of Re approaching infinity. But this is only along a streamline, but if you have uniform approach flow, so in a class of problems where you have uniform approach flow, then one streamline is indistinguishable from another. So, the constant is replaced by a universal constant. So, for a class of problems where you have uniform approach flow like this, you will have p over rho plus u square over 2 equal to a universal constant. But capital U will have both components of velocities, u square plus v square over 2. So, now you can solve Navier-Stokes equations by getting the velocity field from del dot u equal to 0 combined with vorticity equal to 0. These two equations will give you the velocity distribution and Bernoulli's equation will give you pressure. So, this is a shortcut to solving Navier-Stokes equations. So, which is why Euler equations also facilitate simplification. You can get meaningful answers with substantially reduced effort. So, this procedure becomes clear when we look at examples. Okay. So, of course, once you get pressure, you have to integrate pressure like this object. You have an object here, you have to integrate pressure on the surface of the object suitably to get forces acting on it. That will give you all the forces. Why? Because the viscous part, the shear stresses are 0 in the limit of Re approaching infinity. Okay. On the other hand, at low Reynolds numbers, both normal stresses and shear stresses are equally prominent. Okay. So, both have to be factored in, but at high Reynolds number, it is mainly pressure. So, integrate pressure and find forces. Okay. So, let us take a look at so, today we have looked at Navier-Stokes, then Euler. So, we go back to Stokes and work out a small example. Now, the red font, the red color indicates it is important on one hand, but you do not have to worry about it in the exam, because this is flow over a sphere. What would be the appropriate coordinate system? Spherical coordinate system. So, it becomes, the curvature terms become very involved. So, algebraically it becomes involved. Ideas remain, the central ideas remain simple, but the implementation steps become more involved. So, again we agreed some time ago that I will test you on Cartesian coordinates, I will test you in cylindrical coordinates. Spherical we will just talk about. So, you have to write these equations in spherical coordinates. So, what is the solution procedure? The solution procedure is solve for pressure right? Del square p is 0. By doing a del dot of the momentum equation, you got del square p equal to 0. And then substitute this pressure distribution in the momentum equation, get velocity. So, if pressure is known, you will have del square u equal to some function of x and y. What is that equation called? If del square p is 0, it is called Laplace equation. Del square u equal to function of x and y, what is it called? I am asking you because some student came running to me and said, is this not heat equation? So, I assumed that you have some familiarity with PDEs. Del square u equal to 0, del square p equal to 0 is Laplace equation. You agree? You agree. What? Del square u equal to function of x and y. What is that equal? That is not 0. It is some function of x and y. What is it called? Poisson equation. Okay. So, that is also a well studied form of governing equations. So, Krasig's book will give you techniques for solving it. But you have to solve in spherical coordinates. Okay. So, you just to review spherical, this is how spherical is shown in textbooks. X, Y, Z is a 3D space, and this is the origin, and P is any point in this space, and OP. So, R is any point. It is no longer confined to a plane, but this OP will have a projection onto the xy plane. Let us call this P prime, and this angle is theta, while this angle made by the radial coordinate with the z axis is given a symbol phi. So, r theta phi. So, you have to write the governing equations in spherical coordinates. Okay. So, now let us see. This is a sphere, and there is flow from left to right. So, this flow is capital U, and sphere has a radius capital R. Fluid viscosity. So, fluid properties are rho and mu, and conditions are such that Reynolds number is small. That means the diameter is small. So, the diameter is small, small sphere. So, far away from the sphere, the field is unaffected, undisturbed. Approach flow is undisturbed, but around the sphere the field is disturbed, giving rise to forces acting on it. So, if you think of a cross section of this sphere, Let me just show that cross section here. So, you take a plane, you cut the sphere through a plane, and on that plane there will be this angle theta. So, if you treat the flow to be axis symmetric, with respect to theta. So, theta is an angle that is defined on this cross sectional plane. So, the flow is taken to be symmetric. It is a slow flow past an object. So, around on a cross sectional plane, around there is no dependence of the velocity distribution and pressure on theta. And as a result, the velocity component is also 0. So, essentially pressure will depend only on r and phi. So, how do you get pressure? By solving Laplace equation. So, the solution derived originally by Stokes using this procedure, that is, first is solve for pressure and then solve for velocity. So, I am just giving you the solution straight away. So, this is the solution for pressure. Similarly, you can get the solution for velocity . U r equal to when somebody gives you a solution, you can check it very quickly by seeing if boundary conditions are satisfied. Check if, what are the boundary conditions here? On the no slip, on the surface of the sphere r equal to capital R, velocity components will be 0. And away from the sphere, as small r approaches infinity, the velocity components will become consistent with the uniform flow field over there. Uniform flow would be u equal to capital U in the in the flow xz direction here. Okay. Similarly, pressure, for pressure, as you go away from the sphere, surface of the sphere, pressure will become the far field pressure, the undisturbed stream pressure, P infinity in the previous slide. So, from velocity you can find shear stresses, and from pressure of course you will get normal stresses. So, just write down expressions for sigma RR. So, these are all in spherical coordinates. So, the force acting on the cylinder or on the sphere will have lift and drag. Let us look at the drag portion of it. Drag will arise, both forces will arise from a distribution of normal stresses and a distribution of shear stresses. So, force arising from, so this is normal arising from pressure and, or I should say sigma r r. And shear or tangential arising from sigma r phi. Okay, so, if this is a part of the sphere, this is sigma r r, this is sigma r phi. So, since the flow is axisymmetric, you can work with the ring element. There is a sphere and you took a plane passing through the sphere. So, there is a ring element. The ring element can be your elemental area on which these stresses act. So, the force acting on the sphere in the flow direction, that is called drag, and that arising from normal stresses. So, normal stresses will be sigma r r evaluated at r equal to capital R, and sigma r phi evaluated at r equal to capital R. So, this is very similar to the calculation we did for the cylinder. So, normal stresses will give rise to what is called form drag is equal to integral 0 to pi sigma r r at r equal to capital R 2 pi r. I think I have to have a sin phi or cos phi. I think there should be a cos phi. d phi, and the shear stresses So, these expressions now that, so the expressions in spherical coordinates can become a little long, but the steps involved are the same. That means, solve for velocity, solve for pressure, substitute in the constitutive relationship, integrate those stresses on the surface of the object and get the forces. So, drag equal to the form component arises from normal stresses, which turns out to be 2 pi r mu u, and this viscous turns out to be 4 pi r mu u. So, this whole thing is 6 pi r mu u. This is drag acting on a cylinder, on a sphere placed in uniform flow is 6 pi r mu u. So, I think we are out of time. We will revisit very briefly the problem of flow past a sphere, bring it to some closure, and then move on to high Reynolds number flow. Okay. That would be on Monday.